Polar molecules 4.4. Okay, when I say what is a polar molecule, HCl, if you have a diatomic HMCl, we need to look at the difference between the electronegativity. I'm gonna go to the table. If difference between the electronegativity of the two atoms like HCl, right? Now Cl is more electronegative than H. Look at the electronegativity table. The electronegativity of H is 2.1. That's 2.1. And for Cl is 3. So the difference between their electronegativity is 3 minus 2.1. So 0.9. Now the rule is this. The rule is this. If the electronic difference between the electronegativity, just put this here, is between 0 to 0.4, the bound is non-polar covalent. Non-polar covalent. If this is between 0.4 and 1.7, is polar covalent. If this is higher than 1.7, it's ionic bond. The difference between the electrons of HCl is 0.9, of course, is coming between this area. So the bound is polar. Since the bound is polar, you have a partial, the electron wanted to spend more time around Cl, is more electronegative. So the cloud of the electron, if I just draw it, the cloud of the electron going to be here small, and here around the Cl, you have more cloud of electron. That's why HCl, we call this one H, get in partial negative and charges, and H become partial positive charges. This acting like a magnet. We show the vector from positive to negative. So this is the vector showing it is polar, and what is the direction of that polarity? From positive to negative. Okay, for H and H, you know, both of them has electronegativity of 2.1. 2.1 minus 2.1 is 0. So 0 means it's non-polar covalent. PCl, P is 2.1, Cl is 3, the difference is 0.9, so it's going to be polar covalent. NaBr is 0.9, and Br is 2.8, minus them is 1.9. 1.9 is more than 1.7, right? So it's going to be ionic. This is non-metal metal, so you can find that. So you can do question number 1, question number 2 and 3 is homework. The polar molecule. Now here that was diatomic, it was just 2 atoms. Now it's just, if you have more than that, like a shape, it's not going to be simply that you predict that. Like let's say, let's look at the CO2. You know, CO2 is a linear shape. The C is 2.5 and oxygen is 3.5. If you minus it, it would be 1. The bound is polar covalent here and here, but since it's symmetric, they cancel each other, right? Just want to make it bigger. So look at this. It's from positive to negative, right? Here's from positive to negative. As you see, these two vectors cancel each other. I know each individual bound is polar, but it's canceling. So first thing you have to do, you have to determine if the bound is polar or not. The bound is polar. So we go to the next step. We call it, we go to the symmetricity. If this is symmetric, so it's non-polar. If your molecule is non-symmetric, is polar. So here, your molecule is symmetric, and so this one is non-polar. Now H2O. Oxygen has electronegativity. Oxygen has 3.5, right? 3.5 is 2.1. So it's going to be polar bond, right? If you take difference between them, 3.5 minus 2.1, it's going to be 1.4. 1.4 is between 0.4 and 1.7. It's polar covalent. And since we have a lone pair here on oxygen, it's bending. And here is partial pause from positive to negative, from positive to negative. These two vectors, if you put that in a space, they don't cancel each other. That's why the whole molecule is polar. So the bond is polar. You check the symmetricity is not symmetric, so it is polar. So NH3, we know that the NH3 is this shape. We have a two lone pair, that's why it's kind of one lone pair on here, that's why it's bending. Electronegativity of the N is 3 and for H is 2.1, is 0.9. So the bond is polar. We have to check the symmetricity. Since we have a lone pair of the electron on the end, it's not going to be symmetric and push the bond down. So these vectors not going to cancel each other. That's why this is polar. So for the practice, you can do question number 6 and 7.